everyone, and welcome back to the Biochemistry 4024 SI Program YouTube channel. My name is Jess, and I'm one of your content creators this semester. Today we're going to talk about all things myoglobin and hemoglobin, specifically the concerted model for their binding interactions. Disclaimer, if you're watching this at a later date than spring 2024, you may not be learning about the concerted model in class, so be sure to check. So for starters, we all know that we breathe in oxygen and we exhale carbon dioxide. This oxygen is transported all around the body to our cells, and there are two proteins that help to ship this oxygen and carbon dioxide around. They are myoglobin and hemoglobin. Let's first talk about the structures of these proteins. Hemoglobin has 4 subunits, 2 alpha subunits and 2 beta subunits. It has 4 heme groups total, with 1 heme group in each subunit. It can carry 4 molecules of oxygen. Myoglobin has 1 subunit and 1 heme group. It can carry 1 oxygen molecule. So what even is a heme group in these proteins? A heme group consists of an iron in the center of a porphyrin ring. The iron is bonded to a histidine residue and 4 nitrogen molecules as shown. Oxygen directly binds to the iron in the hemoglobin and myoglobin. So let's talk about the differences between these proteins other than their structures. Think myoglobin stands for muscles. This is what carries our oxygen to our muscles. Remember from Gen Chem, mono means 1, so you can remember that myoglobin has 1 subunit and therefore binds to 1 oxygen molecule. Hemoglobin is going to be carried everywhere else in our bodies, in the lungs, tissues, and it even carries oxygen to myoglobin. Let's take a look at our myoglobin binding curve. Notice how it is hyperbolic. Here on the y-axis, we have the amount of myoglobin bound to oxygen. At 0, we have no myoglobin units with oxygen bound to its heme groups. At the top here, all of our myoglobin proteins are bound to oxygen. On the x-axis, we're looking at the partial pressure of oxygen in our muscles. Here at 0, we can say that there's no oxygen in our muscles, and here there is a lot of oxygen available to our muscles. So at the top of this curve here, we can see that myoglobin is bound to oxygen. It is storing it for our muscles. At the bottom of this curve, you can essentially say that myoglobin has given up all of its oxygen, allowing our muscles to use it. So there are not many subunits attached to oxygen here. Let's look at how little oxygen our bodies need in order for myoglobin to be fully saturated with oxygen. Think that myoglobin is very selfish. It wants to hold on and store this oxygen for as long as possible. So we don't need much oxygen in our bodies for this myoglobin to be saturated. Let's compare this with hemoglobin here, which has an entirely different curve. Hemoglobin's graph is sigmoidal. Let's make sense of this conceptually. Imagine that we have just taken a breath of fresh air and our lungs are fully filled with oxygen. Hemoglobin is going to grab up all of the oxygen from the lungs and transport it around our body. When hemoglobin enters the tissues of our cells, our oxygen concentration is lowered. Hemoglobin is not as selfish as myoglobin, and it wants to give up this oxygen so that our body can use it. Hemoglobin will not hold on to oxygen for as long as myoglobin. It will give off its oxygen to cells and muscles. So when we compare our myoglobin graph to our hemoglobin graph, we can see here that at low partial pressures of oxygen, our hemoglobin does not hold on to our oxygen. It gives it away. So why do these proteins have similar structures, but their graphs look so different? This is because hemoglobin exists in 2 states and can change its affinity for oxygen because of its subunit interactions. Myoglobin cannot do this because it consists of 1 subunit. Our 2 states of hemoglobin can be found in the T state, which stands for tense. This means that the protein cannot bind to oxygen. And the R state stands for relaxed, and this can bind to oxygen. The T state and the R state exist in equilibrium, constantly altering between each state. This is what results from a tertiary subunit interaction between the subunits in hemoglobin. This is what we call subunit cooperativity. Let's look closely at what's happening during the T and the R states. In the T state, the iron from the heme group is pulled out of the ring and oxygen cannot bind. In the R state, the iron from the heme group is pulled into the ring and now oxygen is allowed to bind to the heme group. This is from a subunit interaction, changing the affinity for oxygen as we move from the T state to the R state. What exactly determines if our protein stays in this T state or the R state? Well, this is entirely dependent on our partial pressure of oxygen in our bodies. Let's return to our graph. Say we have high oxygen levels in our bodies and we have just inhaled. In our lungs, looking at this graph, do you think that we will favor the T state or the R state if a lot of our hemoglobin is binded to oxygen? It is the R state because we can look at how many subunits are bound to oxygen here. In states of high oxygen concentration, we are going to favor the R state, and our iron is going to remain in the porphyrin ring. Say we have low levels of oxygen in our bodies. Let's look at in our tissues on this graph. We will have low levels of hemoglobin bound to oxygen. What state will we favor here? Well, our hemoglobin is going to favor the T state, and the iron will be pulled out of the plane of the heme ring. Dr. Puritz strongly emphasizes the difference between the concerted and the sequential model. This tertiary subunit interaction is the main proponent of the concerted model, which was explained in class. The sequential model is not supported by Dr. Puritz. We hope you enjoyed the video. Please subscribe so you can be notified whenever we post a new video each week. As always, we look forward to seeing you in the next video.